the other tests that I'm going to be giving you, test 1, test 3, and test 4. I cannot ask you a question on everything I want. What that means is that when I'm showing you a back test, I can't possibly show you all the different types of questions that I could put into it. To emphasize that point, I thought I would start with the study guide. And what? We're going to do that next. All right? But for emphasis, I want to start with this, so that you understand, even though there's a high likelihood that the questions you're going to see from the back test will reappear, there are other ones that are hiding in the study guide that you also need to be familiar with. Let's just go through it right now. Units of concentration, all right? One of the questions I like to ask on units of concentration is convert one unit of concentration into the other, or simply give you grams of solute, grams of solvent, and then say, I want the molality, the weight percent, and the mole fraction. What does that mean? That means you need to know those three things by heart. What is the definition of mole fraction? What is the definition of molality? And what is the definition of weight percent? See this? I'm not going to ask you. This one right here. All right? Not going to ask you. I don't know why I said it, but I did. Moving along. Here is a list of the 5 major types of questions, not counting this, that I can ask on the next test. I can't ask all 5 of them, but I'm probably going to ask 3 of them. Henry's law, Raoult's law, boiling point elevation, or freezing point depression. I always ask one of these 2, not both, and then as osmotic pressure. Also, consider that when you're looking at those problems, you have to ask yourself, is the solute ionic or is it covalent? Meaning ionic, will it dissolve in solution into multiple particles? Because if it does, then you have to use that Van Hoff factor, the small letter I, on the side where the concentration is. If it goes into 2 particles, Van Hoff is 2. If it breaks down into 3. What type of particles am I specifically talking about? Ionic. Here we go, right out of Chem 100. This is an ionic particle. How do I know it's an ionic particle? There's a metal in it. And what does that mean? It means that in an aqueous solution, it's going to dissociate into how many particles? 3. 1 magnesium, 2 chlorines, and therefore the Van Hoff factor for this will be 3. When we do the back test, I'll go over them with you and show you. Think about it. You don't have to worry about the Van Hoff factor. Let's go to chapter 14. We're going to kind of pick and choose. In this first one, concentration versus rate data, I always ask that question. That's the one that's usually more than 20 points. And you've got rate data at the top, and eventually you have to look at the bottom. And at the bottom of the question, does the rate data agree with the mechanism? And we're going to actually do one of those problems on the back test. Always, always, always ask that question. All right? Concentration versus time data. Notice it says table 15.1. It's probably 14.1. when you look at the book. All right, 14.1, they talk about the integrated rate expressions for zero order, first order, and second order. You just gotta know them. All right, write them on your flipping body someplace, and then don't let me catch it. All right, but you gotta know them going into the test. We're gonna do one of those on the back test. The one we're gonna do on the back test is gonna be first order. You could also I could also make it a second order or a zero order, which means you need all three equations. Hidden in that is also the half-life if we're talking about a first order. All right? And I'm going to take a minute to talk about that later. The Arrhenius equation. You know, I love the flippin' Clausius-Clapeyron, right? Right? That's the one with the social disease. The only way to finish it is to ask you the Arrhenius equation also. So make flippin' sure you know the Arrhenius equation. I will tell you that when somebody comes up to me during the test with the Clausius-Clapeyron equation, say, Doc, I think you gave me the wrong data for this problem. The only thing I'm going to do is start crying for you. So please keep it straight. Oh, you're not going to get it right. You're going to lose points. All right. Here you go. Rate law mechanism. This is really a continuation of this. List of equations from the back. Make sure you know those. Let's keep going. What's in bold? Has to be an ice table question. Have to have an ice table question. Make sure you can at least do a calculation of Q to figure out which way the reaction is going to go, either forward or reverse. Here, manipulating chemical equilibrium. That's one of the problems we did on Monday, where we took chemical equations and we added them, we had reciprocals, divided them, multiplied them, double them here, square them there. I love that flippant question. I love asking a question like that on the test, all right? You what? I just love asking a question like that on the test, right? So look at the problems in the book. A lot of them are very, very good. Practice them in order to get on top of it. Disturbing equilibrium is really a continuation of this, all right? It's the use of an ice table, but we're going to use the ice table to disturb the equilibrium, then do a recalculation based upon adding a reactant or adding a product, and then one becomes minus x, the other one plus, work it down, and then finding the new equilibrium constants. So, start with this. Check the test online against this, all right, the one we're going to go over. Anything that's not on the back test, dig into the book and correlate this with questions on the back of the chapter. Because I love to take questions from the back of the chapter, tweak them or tool them a little bit, and shove them on a test. All right. Another place to look is also those problem sets. If you don't see a question you like in the book, or even before you go to the book, look at the problem sets. Some of you are now saying, what the wrong with progressive board? All that information. Just trying to maintain your attention so you can go on the next step. I'm really not that flippant crazy. I am pretty crazy. Not that. All right, here we go. vapor pressure of benzene is at 60 degrees. The vapor pressure at water is at 60 degrees. A 45-gram sample of water, 750-gram sample of benzene, determine the vapor pressure of the mixture at 60 degrees. What type of a problem is this? It's a what? No, it's not a class. All right. I still enjoy hearing it. P0 vapor pressure times X of the solvent is equal to P of the mixture. All right? A vapor pressure problem. I've given you more information than you need. What is the solvent? What is the definition of a solvent? For what? What? The one that is in most abundant. What is most abundant here? Benzene is most abundant. So what is the solvent? Benzene is the solvent. So its mole fraction of the solvent is going to be moles of benzene plus moles of water. And up here you put moles of benzene. That's the mole fraction of the solvent. Did I give you moles? Did I give you moles? 8 grams. Let's see. Is there any way to convert grams to moles? How do you do that? With the molar mass. Are you given any information to convert to find a molar mass? Ah! So do it. Give me the moles. God, you didn't cover converting grams to moles on this test. Do it. Anybody already do it and have an answer for me? Say what? This is C6H6. 6 times 12 is 72, plus 6 is 78. 78 is the formula weight of benzene. Water, the formula weight is 18. So let's put the moles in. How many moles of water do we have? How many moles of benzene? Okay, stop. Let's assume you can do that. Okay? Let's just assume you can do that calculation. Let me keep rolling. All right? 9.6? Okay, thank you. Don't raise your hand and tell me it's 9.5. Look at that number. Is it a large number close to 1? Then you know you've done it right. If you do it wrong, your number is going to be very small, and you're going to be using the mole fraction of the solute. So make good gosh darn sure you use the mole fraction of the solvent. So if you use the mole fraction of the solvent, which vapor pressure will you use? The vapor pressure of the water or the vapor pressure of the solvent? The solvent or the solute? Solvent. So the vapor pressure, not this, but the 400. because benzene is the solvent, and it's going to be a little less benzene, so therefore the vapor pressure will go down. And that's your answer. Let's do the next one.
Just a quick question.
Yeah.
How did you get 0.96? Aren't you supposed to divide 78 divided by 96?
Whatever this is, moles of this, look, I didn't get it. Somebody told me this. I know it's going to be a number close to 1. Whatever it is, look, whatever it is, okay, whatever it is, guys, all right, this is third grade math,
Right, it is.
all right, this number plus this and this, it's going to give you a large number, whatever that is. It's got to be a number less than 1, and it'll be, but it's going to be close to 1. You get it, if you get a number greater than 1, you're wrong. If you get a number that's 0.2, 0.3, 0.4, you're wrong. Questions?
We're good.
Okay. Let's look at problem 2. Look at this. I didn't tell you what the solvent and the solute is yet again. 55.5 grams of benzene. 49.95 grams of water. Determine the boiling point of the water-benzene mixture. What's the solvent? What's the solute? Okay? Yes? Okay. Now, if water is the solvent, then I gotta look at a table in the back. Because I didn't give KFs, KPs, K anything there, right? Change. What are we changing? Changing the, change the temperature for boiler. Delta TB is equal to K PB times the molality times our Van Hoff factor. Is there any metals here? Any metal there? Is there any metal here? Is anything going to dissociate? What's the Van Hoff factor? It's 1. It's 1. It's 1. Got to go to the back of the test. Say that again. Okay. Thank you. Just look at this. You got KDPs, you got KFPs. You've got water, you got benzene. You have more data here than you need. You got to pick the right stuff. You got water and you got benzene present. Which KV, because it's a boiling point, right? Which KVP you're going to use, the first one or the second one? Because water is the solvent. Then you're going to plug the molality in. Okay? Going back. .5 is divided by the formula weighted benzene, which I said was, and per kilogram, which is 0.49. Yeah, go ahead. 4995 kilograms. That'll get you the change. phi, that's the Van Hoff factor. Not a problem. Change in the boiling point. Okay. Change in the boiling point. Let's assume. I don't know what the answer is. What'd you get? No, I need that. I'm jumping to that. 0.73. 0.73 is the number they came up with. All right? Don't tell me it's something else. Determine the boiling point. Answer, 0.73 degrees centigrade. Is it correct or is it false? All right, 0.73 degrees Kelvin. Am I getting any closer? What do I have to do with that 0.73 degrees? Do what to the boiling point? Add it to the boiling point. Boiling point elevation. So your final answer must be 100 plus 0.73 is equal to 100.73 degrees centigrade. Do not forget to take the delta. In the case of the boiling, you add it because it's boiling point elevation. If it was freezing, it is a freezing point pressure. You subtract it. Questions? Where are you going to get the boiling points if you don't know them? Back here. Point being, wherever possible, I do not like to give the constants because then you put in the equation to fit the constants, like you're going to the supermarket. I like to put all the information necessary on the back so that you pick the equation and find the constants, not start with the constants and pick the equation.
You're not giving us the equations.
I'm not giving you the equation, and you got to figure out the constants also you're going to use. Will they be something? They'll be on the back, but you got to know what you need. This isn't Chem 100 where everything is handed. You got to know what you need to get the problem solved. It'll be on the test, but it's not going to be spoon-fed within the problem, particularly when it comes to constants. All right, let's continue. Problem 3. A 1.005 gram sample of an unknown biomolecule is added to 1.195 mils of water. The biomolecule has an osmotic pressure of at 25 degrees centigrade. Determine the formula weight. I is equal to CRT. That's the equation. What is P? What is pi? Is the osmotic pressure. Pi is the osmotic pressure. The osmotic pressure in what units? Do you need to convert this to anything? Just leave it in atmospheres. Point, whatever it is over there. 0.018 atmospheres. Let's leave C blank for the moment because we need to get the formula weight. And formula weight is in there. What value of R are you going to use? Right, 0.082, whatever. I know it's that because here are the atmospheres. The liters are over here. 25 plus 273 is the degrees Kelvin. Liter atmosphere, moles, degree Kelvin. And because I know the units for R, I can figure out what the units for C are. There's moles per this is equal to moles per liter. So you get R. So you get X, okay? Whatever the number is. X is equal to moles divided by the what? Liters. Okay. X is equal to. Do we know how many liters of water we have? Yes. And we can convert them. 0.001195 liters. Do I know how many grams I have? Yes. What do I get in here? And what am I looking for? Formula weight. X is for. You see how to solve the problem. The reason I asked you to solve the problem like this is because this is what we use osmotic pressure for. We use osmotic pressure and use osmotic pressure as a means of determining the formula weight. Determine a formula weight with three different techniques, and by God, you know the formula weight of an unknown biomolecule.
What do you put under there again?
Under where? Here?
Yes.
J. It's unknown. That's what you're finding.
That's what we're looking for.
So what's the answer gonna be? It's gonna be in moles?
No, it's going to be in grams per mole. Units of formula weight. Units of formula weight.
I'm trying to figure out how everything crosses out, where you end up with grams per mole. Like I see, tell me what
This is in moles per liter. Grams divided by the formula weight is moles, and that's so moles per liter is equal to moles per liter. You could simply say the formula weight is equal to whatever the number is, grams. Formula weight, molecular weight. What? Sure, call it grams per mole. That's okay. Not grams. Look, this grams and liters are only the same thing when you're talking about water, because the density of water is 1 gram per milliliter. All right, let's continue. You've seen how many versions of this problem? Okay? If you don't study this, do me a favor. When you turn the page and you see this problem on the desk, I want you to take your forehead, wrap it on the desk, and pre-mark the page for me. All right, just leave it the flip blank and put a big 0 at the top of the page if you don't study. All right, but first, just so that I can anticipate how quickly I can get done with the paper, just go like this and wrap the desk. So I said, ooh, that's one I don't have to grade. All right, first thing, determine the order with respect to. All right, what's the first thing you should put down?
the rate law.
Right, the rate expression, rate law. It's all good. Rate is equal to K times F. What kind of F? Just that F. F negative. All right, today you want to use A? All right. And oh boy, here we go. C 3 BR, right? All right. To the down someplace. Put it down at the very top. Determine the order with respect to F. What variable up there am I trying to find? Everybody agree? If you're going to find A, then you want to pick two conditions where the concentration of A is changing and the concentration of the alkyl halide is not changing. What are the two conditions? I'm going to check you. Here it's doubling. Here it's not. Good. Good. I'm going to set it up. I already know the answer. 5.8 times 10 to the minus. What is it? Minus what? Somebody give me. Make believe you. 8. Thank you very much. Appreciate your courtesy. 5.8 times 10 to the minus 8. This is 1. We said 3 or 2? 2 equals K over K F 0.75 1.5 times 10 to the what? Thank you, sir. Over here, this is to the A, this is to the A. And I see that it's going to be did I do that right? Yeah. 2.25? No. Something's wrong. F has got to change.
Why did you get an initial rate?
Hold on. F has got to change. If F is going to change, 1 and 3. 1 and 3. 1 and 3. 1 and 3. So 1 is 2.25. 2. And this is 4.54 times 10 to the negative 6, and then the other ones are going to be fixed at 0.75. 0.75 times 10 to the minus 4. Is it 6? Okay, 6. B. Look, the rate's got to change, doesn't it? 2, 1, and 2. It's 1.1.
You made the initial rate the same, and on the example, alpha accident.
Look at 1 and 2. Just looking at 1. No. Stop. 1 and 3. The rate didn't change, did it? Okay. But the concentration of this did. So watch. 1 is equal to, cancel. 1 over 2 to the A. What must A equal? 0. It's 0 word. No mistake. Next, 1 and 2 now. 5.8, 1.16 times 10. The rate's changing here. So I know it can't be 0.
That is always the case, right? If the rate doesn't change, it's always going to be 0.
Correct.
So,
But I gotta see something.
Okay.
All right. Otherwise I think you've taken it and turned it into an optometry exam. Is equal to, drops out 1 over 2 to the B. What is B equal to? So it's first order with respect to the alkyl halide. Correct? Okay. So the rate law, here's the rate law. 0 and 1. If it's 0, you don't have to put it in, or you could put it in with a 0. It doesn't matter. It means the same thing. Yes?
Professor?
Yes. Yes.
How do you know which experiment to use?
How do I know what?
Which experiment to use? Like one.
Okay. Watch. I want to determine the order with respect to the F. If I'm going to do an experiment, I want to keep everything constant except for the one thing I'm going to study, which is F. So F has to change, and the other one can't. How do I do this one? Well, determine the order with respect to that alkyl halide. So, whenever you do an experiment, everything remains constant except for the thing you're studying. So I need this to change and this to stay constant. Determine the rate law. This is the rate law for the reaction. Okay. The next two. How do I figure the rate constant? Any of them, 1, 2, or 3. And plug it in, 1, 2, or 3. Because you know this is 0, you know this is 1. So put these two concentrations and the rate in for 1, 2, or 3, and you will get the K.
But if it's 0, it drops out, right?
Right, so you don't even have to put it that in. You could ignore the concentration of this now that you know it's 0. But yours may not be 0. Okay? I'm leaving it in because when you do this, the data that I'm going to give you could have both of them being first order. So to be pedantic, I'm leaving it here so that you realize you don't automatically drop one out. It's only a function of the fact that this is 0 order, correct? Everybody's following me? Okay. Determine the initial rate for experiment 4. What do you need to do that? You need to find K first. Did you find K first? Where did you find K first? Right above it. So you take the K that you just found, and look, let's go back to experiment 4. You just found the K. Here's the concentration of F. Does that matter? No. Here's the concentration of the alkyl halide. Does that matter? Plug in the K. One number times the second number is equal to the third number, which is your answer. You plug the 1.75 in here. 1.75 times 10 to the minus 6th in here. Here, I don't care what you put in here, right? You put your mother's birthday in there for all I care. K, you just figured out. One number, there's the rate. Here's the rate. Yes. A is anything, is the order. A is K is the rate constant. This thing, K, it's the rate constant. That's the rate constant. It is a constant that allows you to equivocate concentrations with the rate of the reaction. Like the density. It's a way to equivocate the volume and the grams. Moving along. Questions? Questions? This is a mechanism. Yes. I can't hear you. Did I do what? I absolutely did C. C is this. I want to erase the variables and put those in. Shh. Shh. I'm running out of time. I won't finish the test. This is a mechanism. A one-step mechanism. Therefore, this is the rate determining step. If you see an arrow moving like that, it is the rate determining step. If you see an arrow going in two directions, it's the fast step. It means you're at equilibrium. But if the arrow is in one direction, it means it is the rate determining step. You need the rate determining step because that is the step that you come up with the rate law based upon the mechanism. That's the place you go to get the rate law based upon the mechanism. This is the rate law based upon the kinetic experiment. So, rate is equal to K, the rate constant, times something. Times whatever. Here it is. F is a reactant that affects the rate. And here's the CC with the BR and a whole bunch of N, which also affects the rate. That's what these two things mean. Here is the rate law from the mechanism. Here is the rate law from the kinetics. Question 1. What is the molecularity of this mechanism? Is it zero order? Is it first order? Is it second order? Is it third order? What is the order? That's what molecularity means. What is the order? Order. Where have I heard that word before? Determine the order. Too loud? I'll stop. Come on. This is first order. Zero is 1. Get it though. So that's first order. Okay. Take a look at this. What's here? 1. And what's this? Okay. Calculators. 1 1 is 2. So the order of this is correct. The order of this is. Do they agree? No. Also they don't agree because fluorine doesn't affect the rate. Doesn't affect the rate here. And fluorine does affect the rate here. Where did I get to it? I'll show you. The mechanism tells me, because this is the rate determining step, that this is necessary for the reaction to occur, and this is necessary for the reaction to occur. That tells me that if I increase this, the rate's going to go up, or I increase this, the rate's going to go up. Therefore, both of these appear in the rate law from the mechanism. It's more complicated than that.
I was going to ask, so if F wasn't in that equation, if it was simply, whatever that GR crack, whatever, and then splits it into 2, then it's going to be a first order, right?
If it was this, then it would agree. Okay? Is there F here? Is there any F here? Is there any F here? The rate law for this looks like that. Take out the F. They're in complete agreement. The one over there, both of them are present in the rate determining step. Therefore, they have to be present in that. Go to the back first.
So for the rate law from the mechanism, is that where the exponents come from the coefficient?
The exponent from the coefficients come from the number of times these appear in the rate determining step. Yes.
So for the rate constant of the reactions going backwards there, so
The
that
rate To a degree.
Four times, right? I'm sorry, square.
It would be square. It would be square. All right. So, does the rate law for this agree or disagree with the rate law for the kinetics? Disagrees. Okay. Let's keep going. Please get here early on Monday. Look how long it's taking me to go through the test. You're going to need every flipping minute. If you come late, you'll be rewarded. Not in a good way. Right and equal. All right.
Doc, while you're racing, can we please meet up again today or tomorrow and do more of these comments?
When I get to the very end,
Okay.
I'll
I would love
Yes.
to.
all right. Probably tomorrow.
Tomorrow, Saturday.
Tomorrow, probably around 5-ish in the afternoon. All right. Write an equilibrium expression for this reaction. Chem 100. I'm going to do it in 3 weeks. K. K is equal to reactants or products go at the